Alright, so in this example, we're asked to estimate the melting point of ice under a given pressure, and we're given some assumptions that we can make, and we're given some data that we're given. So the main thing that you need to realize here is that we're dealing with a change here of a solid to a liquid. And whenever we're dealing with this change, then the equation that we need to use is no longer the Clausius-Capeyron equation, but it's actually this equation. So the one that is sort of just given in the notes. There's no real explanation given for it. It's just more explained that for when the solid liquid boundary, it's stated that the equation used is this one. It's not that, it's the change in the molar volume of fusion that's there below the line. So the most important fact is that you understand the distinction between when we're dealing with solid to liquid changes or liquid to solid changes, then we use this equation, or when we're dealing with liquid to vapor or vapor to liquid transitions, then we're dealing with the other Clausius-Capeyron equation. Right. So that's what we need here. And of course, it says estimate the melting point of ice under a pressure of this pressure. So we're given a pressure, and then we're given the mass or the mass density of the liquid and the solid under those conditions, and then we're also given the enthalpy of fusion at the normal melting point. So in other words, we're given the fact that we can use we can always use the normal melting point or the normal boiling point, for that matter, at the Clausius-Clapeyron equation as the other set of conditions. So we essentially have everything that we require. The only thing that we need to really look at is to calculate this delta, or this change in the molar volume of fusion. So in other words, what is the change in the molar volume during this fusion process, or diffusion process, because it's like the melting process for the ice. So basically what we need to use here is the fact that molar volume is defined as the molar mass of a substance divided by its density, right? By its mass density. So, I mean, the unit makes sense because you have grams per mole and grams per mass, and then you're left with the grams will cancel, and then you have mass per mole. So in other words, you'll have your molar volume. So if we want to calculate the change in fusion, or the molar volume of fusion, then it will simply be the molar volume of our liquid minus the molar volume of our solid, which is each equal to the molar volume of water. So I mean, that will be constant, but anyway, over the mass density of the liquid minus the molar volume over the mass density of the solid. Right, so that's the starting point of this entire thing. Okay. Also, we need to calculate estimate the melting points. In other words, we're interested in T2. So in other words, if we take T1 and P1 as the normal conditions, so in other words, the standard conditions, so T1 and P1 is, 1 atmosphere, and the normal melting point of ice is what it is, 273.15 Kelvin. Then we want to calculate T2, so we just have to rewrite that equation. So then we also have the change in the molar volume, right? So let's rewrite the equation quickly. Basically, we're going to take P1 over, so then it becomes P2 minus P1. We need to flip that entire quotient, and then T1 just goes over the line, so it becomes plus T1. So then T2 will be equal to T1 plus P2 minus P1 times the inverse of our quotient. So in other words, it will be T1, the change in the molar volume of fusion, divided by the enthalpy of fusion. Okay, and we have what the molar volume of fusion is. We wrote that just above there. So P2 minus P1, T1 over the enthalpy of fusion times molar mass of the mass density of the liquid minus the mass density of the solid. Okay, so we have that. Then of course we can take out this mass density value here commonly, so it just becomes over 1, and then the mass density is, or the molar mass, my apologies, is over there. Okay, because the molar mass is constant for those two. Okay, so then we just have to plug in our values. So T1, so all the ones is the normal boiling points or the normal melting points for water. So the normal melting point for water is of course 0 degrees Celsius, so that's 273.15 Kelvin. That's something we assume you know. Then the pressure that they give us, so P2 is the pressure at which we're estimating the boiling point, so that's 10 megapascals. So 10 times 10 to the power 6, mega means 10, pascal minus, so normal melting point, so that's of course in terms of pascal, that would be 1.01325 times 10 to the power 5 pascal. Then we have a factor here which is T1 again, so that's 273.15 Kelvin times the molar mass of water, which is, if we quickly look on the periodic table, it's 18.0158 gram per mole. Okay, divided by the enthalpy of fusion. They give it as 6.008 kilojoule per mole, but we want to work in joule per mole because we're working in only Pascal, not kilopascal. So then we want to we work with 6008 joule per mole. Right, that's that factor. And then we have 1 over the mass density of the liquid. So the liquid is 0.99, so I'm just going to quickly write something here, 0.998 gram per cubic centimeter, but we want to work in cubic meter, of course. So we need to rework that to cubic meters. So in other words, so just rewrite this in terms of, so we have gram per cubic centimeter. So we have centimeter on top here, and we have meter here. We want meter cube. How many centimeters is there in a meter? There are 100 centimeter in a meter. So in other words, we need to cube this. So that means we need to substitute in here 0.998 times 10 to the power 6 gram per meter cubed. Alright, and then we do the same for the mass density of the solid. 0.915 times 10 to the power 6 gram per meter cubed. Okay, just in case you didn't follow this, remember, if you're working with the units, then you can write it like this. So you just follow it nice and easy. You put the cubes where they are, so in other words How I got that is if you have 100 cubed, it becomes 10 to the power 6. You multiply it by that, and then you know what the factor is. So the centimeter cubes cancel out, and you're left with per meter cubed and a factor of 10 to the power 6. Okay, that then leaves us at 273.15. Everything here will cancel. We're going to have grams cancelled. We're going to have then Kelvin, mole will cancel. So we're going to have Kelvin, joule, meter cube, Pascal, and then a Pascal will cancel with the joule, joule per cubic meter, because a Pascal is a energy unit per cubic meter. Alright, so that is perfectly fine. So then we just need to, so this works out as 7369335,947, which is then 272.4130664. Okay, Kelvin, of course. So if we take that to degrees Celsius, so in other words, and we have 10 megapascals as our lowest number of significant figures. So taking that to degrees Celsius gives us minus 0.74 degrees Celsius. Right, so if we place ice at a pressure of 10 megapascal, then we will lower the melting point of ice to minus 0.74 degrees Celsius. Just interesting. And does that make sense? Probably because because of the hydrogen bonding structure of ice, we will condense the ice structure. So in other words, the molecules are closer together. In other words, heat transfer can happen more easily, and so the ice will have a lower temperature at which it could melt, which makes sense. So it's just a short interpretation of what the result actually is. Remember, water is the only exception we have to the negative slope on its phase diagram. So because of its open hydrogen bonding structure that it has. Okay, so now by the higher pressure, then it forces those gaps, or those intermolecular gaps, to be a bit smaller, and then it can of course influence the conduction of heat in those gaps, lowering the melting pressure or the melting temperature of the solid, as we see here. So I mean, that's exactly what we calculated. Okay, so basically, just to recap, remember, if we're working with the solid liquid boundary, then you need to use this equation, and to calculate the fusion or the change in the fusion volume, or the molar volume of the molar volume change, then you have to work with the molar volume, the molar mass divided by the mass density will give you the change in the molar volume of the. Right, maybe just a final word on the molar volume, or the molar volume change, just so that you believe me in terms of this equation. So just checking the units. So for molar mass and for mass density, remember the molar mass is in gram per mole, and the mass density is in gram per, well, volume unit. So let's just use the centimeter cube, so just gram per mole. And then of course the gram cancels out, the mole goes below the line, and the centimeter cube goes on top. So we have then centimeter cube per mole, which is then your molar volume. So it gives you a volume per mole. So in other words, it will give you, for example, we have 7 liter or 7 centimeter cube per mole of the substance, which is exactly a molar quantity, or a molar volume of a substance. So that proves how so you can always check with the units that you're calculating the correct thing. All right, so I think that's quite easy in terms of application. It's not really. It's very straightforward. It's just a calculation. Maybe with the mass density, I mean, it's not that. It's like I've really given you all just everything just to calculate it directly with. It's a little bit with the mass density, and you just had to realize we're working with a solid liquid boundary, so you can't use. You had to use this equation instead of the other one. But yeah, other than that, I think it should be fine.